Hi, ladies and gentlemen. Thanks for your interest in our work. My name is Jun. I'm a fourth-year PhD student in Indiana University, Purdue University, Indianapolis. My recent research interest aim to improve the robustness of graph neural networks on non-stationary graph via Bayesian approach. Today, I'm going to present our recent work, defending graph neural networks against dynamic graph perturbation via Bayesian self-supervision. Graph neural networks have been widely used on node classification tasks on graph data. Here we use online social network as an example, as presented in the figure right-hand side. Online social network is a kind of dynamic graphs whose graph structure change dynamically over time. In this example, new users are growing over time. In online social network, GCN-based node classification can be used for user profiling, such as clustering user into different groups for future advertisement or recommendations. However, temporal change of label scarce graphs makes GCN vulnerable to adversarial attacks on any nodes at any time. We denote such adversarial attacks as dynamic graph perturbations. In this paper, we aim to improve GCN's robustness in present of label scarce perturbed dynamic graphs. In this paper, we categorize most existing defending methods into 4 groups. The first one is adversarial training method. This method improves the robustness of GCNs by training with adversarial samples. However, this method can barely train a robust model under the circumstance of extensive label scarcity. To overcome label scarcity, a kind of self-supervised learning method, namely pre-training, constructs a pretext task to help GCN learn transferable graph representation through the pre-training stage. But it is still a challenge to decide a generalized pretext task that can be beneficial to arbitrary downstream tasks. Self-training is an extended form of pre-training. It assigns self-generated pseudo-label to highly confident unlabeled nodes and then adds these nodes to the set of labeled nodes for the next training iteration. However, accurate assignment of such pseudo-label may suffer serious degradation when the graph is undergoing dynamic graph perturbations. Topological denoising method prune suspicious edge on the graph before feeding this graph into the network. Such methods are not efficient on dynamic graphs as the graph structure is always changing over time. Mechanism design method mainly propose a message passing mechanism, also known as graph convolutional operator or node aggregator, to better classify the nodes. Such a mechanism sometimes highly depends on heuristic exploration. Learning graph representation with noisy label is a potential solution to mitigate these issues. In this paper, we assume that noisy labels include both manual and notated labels and auto-generated labels. We argue that such noisy labels assigned to the vertices could be regarded as a kind of self-information for each node, which can help GCN to retrain its performance under dynamic graph perturbations. In fact, usage of noisy label is a kind of defense which is equivalent to recovering the originally labeled distribution of a node and a perturbed graph, for which the node's label distribution has undergone a change due to perturbation. This intuition inspires us to propose a Bayesian self-supervision model, which recovers the original label distribution iteratively to improve the robustness of a GCN-based node classifier against dynamic graph perturbations. Our model has 2 advantages. First, our model can effectively recover the prediction of a node classifier against dynamic graph perturbation. Second, the experience verified that our model can affirmatively alert such perturbations on dynamic graphs. This slide displays the total process of our model. Given an undirected attribute graph, our model classifies the nodes with manual annotated label at first and then generates both categorical distribution and auto-generated labels. Before the inference, our model computes a warm-up label transition metric by using prediction over the chain graph. The inference includes two stages. In the warm-up stage, our model applies gibbs sampling to sample the inferred labels with the warm-up label transition metric. After the warm-up stage, our model samples the inferred labels with the dynamic label transition metric. This dynamic label transition metric iteratively updates in every epoch. For recurry, our model iteratively retrains the node classifier to update its parameter. For alert, our model applies one-time label transition with auto-generated labels. The inference ultimately converge approximating the inferred labels to the latent label as close as possible. In brief, our goal of the model is to sample the inferred label by supervising the categorical distribution based on dynamic conditional label transition, and ultimately approximates the inferred label to the latent label as close as possible. In this slide, we present the experimental settings. Our experiments are conducted on 5 public graph datasets. We assume that the chain graph contains manually annotated labels, but the validation and test graph don't. To simulate dynamic graph perturbation, we execute node-level direct evasion non-targeted attacks on links and features of the nodes in dynamic graphs. We compare our proposed model against 7 state-of-the-art defending methods. The result indicates that the defending performance of our model is superior to competing method in dynamic graph circumstance. We also share our observation on some competing methods. First, adversarial training gets unfavorable performance across all datasets, which reveals that simply using adversarial samples to train the node classifier has limited contribution to the defense. Second, our GCN performs poorly in comparison to adversarial training with the density of the graph increases. Because our GCN adopts a sampling in a hidden representation, whereas this sampling may lose more information on denser graph. SVD approach obtains lower accuracy than JCAP across all graphs, as SVD is tailored to fit the target attacks and may not adapt well to the non-target attack. GRAM has worse performance on Cora. One of the reasons is that GRAM assumes the graph satisfies the homomorphism property. This assumption may break when the graph suffers serious perturbation. Pro-GNN is superior to JCAP on denser graph. We argue that Pro-GNN can simultaneously update the graph structure and the parameters of the node classifier with the low rank and feature smoothly constrained. Such an update reaps huge fruits for recurring better graph structure on denser graph. Furthermore, we visualize our defending results on the test graph of Cora as an example. The visualization clarifies that our model can recover the prediction after perturbation as close as that in a clean environment. The experiments verify that our model can alert the perturbation on dynamic graph. We use ROC as the evaluation metric. The result shows that our model achieved robust alert on top of GCN across all datasets. We analyze the runtime between defense and alert. The unit runtime maintains a comparable level as the size of the graph increases, which indicates that the size of the graph doesn't affect the speed of inference. The average runtime of defense is slightly higher than that of alert in most cases. This is reasonable because our model iteratively trains the node classifier in denser defense scenario. Overall, this analysis illustrates that our model retains a stable speed of inference regardless of the size of the graph. We select GCN as the node classifier and conduct the analysis of two hyperparameters, WS and retrain, on the validation set. We fix the number of inference epochs as 100 and then apply grid search to look for the optimal parameters. The result turned out that WS and retrain reach the optimal nearby 40 and 60 respectively. Both larger and smaller WS have a negative effect on accuracy, and this property also applies to retrain. We conduct an ablation study to examine how the retraining and the update of dynamic transition metric can help our model. In the first two scenarios, the accuracy has no change without dynamically update the transition metric. In the last two scenarios, we noticed that the retraining the node classifier can help increase the accuracy further. This study reveals that dynamic transition metric is a crucial component. Retraining can further promote a robustness of the node classifier with the help of dynamic transition matching. In this slide, we will discuss the limitation of our model and future directions. First, the inference depends on the warm-up label transition match, which is built with the categorical distribution on the train graph. Such dependence indicates that our model can only handle the evasion attacks at this point. In the future, our model can be improved to defend the poisoning attack by iteratively updating the auto-generated labels. Besides, this update may benefit the node classifier under the label scarcity scenario for self-training purpose. Second, our model can only alert the perturbation in this version. In the future, such a version could be extended to detect the anomaly nodes on dynamic graphs. For the community impact, many existing defending methods confront the adversarial perturbation from the perspective of topological denoising and message passing mechanism. The low-hanging fruits from these two aspects have been widely explored. On the contrary, our model improves the robustness of the node classifier by recovering the node distribution. Also, incorporating self-supervision into the defense of GCNs is a promising direction in the recent 2 years. Our work provides an innovative alternative in this path and could be a baseline model for the above-mentioned future direction. In conclusion, we generalize noisy supervision as a subset of self-supervised learning method. This generalization regards the noisy label, including both manual and annotated labels and auto-generated labels, as a kind of cell information for each node. The robustness of the node classifier can be improved by utilizing such cell information. We then propose a new Bayesian self-supervision model to accomplish this improvement by supervising the categorical distribution of the latent labels based on dynamic conditional label transition, which follows the Dirichlet distribution. Extensive experiments demonstrate that our model can not only affirmatively alert the perturbations on dynamic graphs, but also effectively recover the prediction of a node classifier when the graph is under such perturbations. These two advantages prove to be generalized over 3 classic GCN across 5 public graph datasets. Thank you.